Welcome back, students. Today we are going to finish discussing the particle in the box model and apply it to a couple more systems involving electrons, mainly focusing on electron tunneling. Before we get to tunneling, however, we want to first look at one last application that's going to be a way in which we can explain conductivity and why certain materials are conductive and other materials aren't. Then we'll look into electron tunneling, and at the end we'll describe the application of that, scanning tunneling microscopy. So first, we want to look at this idea of conductivity. And I think you guys are pretty aware of what conductivity is. Essentially, some materials are very good at conducting electrons. So you can think of copper wires in which the electricity passes, from the generators into the outlets that we use it in. And for some reason, copper is very good at conducting electricity, and other materials are not very good at conducting electricity, and those are called insulators. So what we're going to do to model this is treat our materials as if they are boxes. So what you can see here, and we'll look more into this later, but this is like the electron potential of the nucleus. And so what we have here is kind of a bunch of atomic nuclei stuck together as we have a bunch of atoms in a metal. And what this does is it creates a box that the electrons can go through. And I think you guys probably remember going back to probably even high school or Gen Chem, we have this idea of metallic bonding, where the electrons are kind of free to roam about the metal. And that's because we have all these atoms, these nuclei close together, which makes for essentially a long box that our electrons can pass through. And this is, of course, only for the valence electrons. The core ones are going to be held more tightly. Now, how can we explain that some of these materials are conductors? And it's a little bit hard to see in this graph, but the way that electrons will add in, especially when you have all these atoms packed in on each other, is you have these bands. So this would be a valence band, and in green here, it's shown that it's fully occupied here. And then you have a band gap. And so this would correspond, say, to be the distance between maybe a 1s and a 2s orbital. So the 1s electrons are full, but the 2s electrons aren't full for a metal like sodium. If we look over here at an example of an insulator, and you can see the fullness again, but there's this emptiness here that is not a band gap. So the band gap is up here at this dashed line. For an insulating material, there is a full conduction band up here. So we can't actually have electrons moving around in this band because it's full. Now, what happens when we apply an electrical potential? That is, we try to send electrons through the material. Again, here we can see a different example of this without an electrical potential. And when a potential is applied, right, so we put a positive side on this end, that makes the electrons, the negatively charged electrons, to be lower in energy if they're at the positively charged end. So we represent that by drawing these lines. Instead of being horizontal, they're now diagonal. The energy is lower on the right side than it is on the left side. And what's going to happen if you get this, of course, that you're going to have electrons up here that are at higher potential energy are going to flow down to the lower potential energy, and you get a net movement of electrons, and that's what's shown here. So this is an example of a conducting material. Now, a non-conducting material, an insulating material, would have this entire band gap full. So even though it would be lower in energy for electrons to move down, there's nowhere for them to move down to because that material is full. And that is one way, again, we can use this particle in a box model to try to explain something that we are aware of, namely that some materials conduct electricity and other materials do not conduct electricity. Okay, so that's the one last example before we get into tunneling. So now we want to explore this idea of electron tunneling. I think you guys are probably somewhat familiar with this idea, even if it really is in only a sort of pop science way. So we'll go ahead and discuss it. Before we talk about tunneling, we want to talk about how a quantum mechanical particle will react with interact with an energy barrier. And the tunneling is going to be, again, an extension of how these particles interact with energy barriers. So we can imagine an electron that we shoot through some energy barrier. So here we have some sort of capacitor that generates an electric field, and that's going to modulate the energy of our electron. And we can depict that in our kind of box model like this. So instead of having an electron in a box, we now have a free moving electron and then a free moving electron with some potential, V naught. So potential in our two regions are constant, but they're different. So we have a zero potential and then we have a higher potential V naught. So we want to ask the question of what do we expect to happen to this electron? And classically, what we would expect, and what, again, what sane people would expect, is that it would have some speed here because it has a total energy that's only kinetic because there's no potential. And then when it crosses this barrier, it now has a potential energy. So some of that total energy has gone into overcoming the potential, and its speed will have slowed down. And that's what we would expect. And that is, of course, somewhat true, and only somewhat true for quantum mechanics. So we'll see that just like our particle in a finite box had a small chance of being outside of the box in a region it shouldn't be, our electron also has a small chance of being reflected by this energy barrier that it should have enough energy to overcome. And we can describe that with again, using our Schrodinger equation. So in both cases, we have a function in which we need to take two derivatives of that function and return that function multiplied by a negative constant. So like before, the solutions we have are either the trigonometric solutions or the imaginary e to the ix solutions. And because our particle is not confined into a box, it makes the math easiest if we choose the imaginary solutions. So our solutions to the wave function look like this in our two regions. We have, in the first region where the potential is 0, we have a e to the ik1x plus b e to the minus ik1x. And here our k1 is reflecting the fact that we only have the energy value here, that's the total energy. We don't have the potential included. Now, this, again, our two functions here correspond to movement in the forward direction and movement in the reverse direction. And we can't rule out movement in the reverse direction once we interact with this barrier. However, after we have crossed the barrier, there's no force acting upon our particle that we'd expect to turn it around. So we do not have reverse direction after we have crossed the barrier. We only potentially have it in the forward or on the left side of the barrier. And so on the right side of the barrier, our wave function can be written as c e to the ik2x, where now k2 corresponds to a slower speed because our energy is lost the potential energy it took to cross this barrier. All right, well, how do we solve this problem? Like we saw on Friday's homework, we have to enforce the boundary conditions, namely that our wave function for the first part is equal to the wave function for our second part at this barrier. And we'll also incorporate the first derivative because remember the second derivative has to be well behaved. So the first derivative must also be equal at those points. So we can go ahead and evaluate that. So the boundary conditions that we want to enforce are shown here. We need the wave function at point 0 to be equal on both sides, and also the first derivative of the wave function at point 0. So to apply this, we just go ahead and substitute these into our equations. So remember our equations that we have are a e to the ik1x plus b e to the minus ik1x. And then we have c e to the ik2x. So we can substitute these values in and set these equations equal to each other. And for the first part, we'll get a e to the ik1 times 0, which is of course just a, plus b e to the negative ik1 times 0, and then that's supposed to be equal to c e to the ik2 times 0. So this simplifies into a plus b equals c. Then for the second part, we can take a derivative and we get the following. So if we take derivatives, we get a times ik1 e to the ik1x plus b, or I guess actually minus b ik1 e to the minus ik1x. And that's going to be equal to c ik2 e to the ik2x. And of course, if we plug in x equals 0 for these, the exponential terms are going to cancel out. And then we'll end up with AIK1 minus BIK2 equals, or CIK2. Sorry, this is BIK1. And the imaginary numbers will cancel out, and we'll get AK1 minus BK1 equals CK2. And we'll write this as the following. We'll pull out the K1, and we'll say that C is equal to K1 over K2 A minus B. So now we want to, okay, we kind of have what these constants are. How do we put them together and, solve for how likely our particle is to be reflected? To determine how many particles are going to be reflected, it turns out we have to multiply the wave functions, right? So the wave functions are a probability. That's weird. They're a probability with respect to distance, right? That's what the square of our wave functions are. And if we multiply that by distance with respect to time, the speed, we end up with a probability with respect to time. And so if we do that, and the way we're going to do that is multiply things like the square of our wave function, which is going to be the square of these constants, by the speed, which is our k's here. And that's going to determine how often we are, or how likely we are to be reflected or transmitted past this barrier. So our percent reflected here, we'll denote that as a capital R. And that is equal to the number of particles that are reflected with respect to time, divided by the total number of particles, the incident particles, with time. And of course, to get this, we want to multiply the square of these constants times the speed at which they're moving. So what I mean by that is the number of particles reflected, that's determined by this B constant. And it's, of course, it's the square of the magnitude of our B constant. So we'll say B star B is the total number of particles reflected. To get that into a per time basis, we need to multiply by the wave vector K1, which is the speed at which they're moving. And then the incident per time is, of course, A star A times K1. Now, if you're thinking carefully, this K1 isn't really a speed, but the way that K1 converts into the speed, everything else is the same. So the K1 contains all the differences between the speeds, so we can use that here as a substitute for speed. And this gives us, since they're moving at the same speed, it gives us B star B over A star A is the percent reflected. So what do we do with this? What we're going to do is relate these two expressions here, and this will give us B in terms of A, so we can eliminate some of these constants that we don't know. And so by doing this, we get A plus B is equal to K1 over K2 times A minus B. And another way we can write this is that it's equal to K1 over K2A minus K1 over K2B. So what we're going to do is we're going to try to solve this for B. So we'll pool the B's on one side and pool the A's on the other side. And in doing this, we will get minus A plus K1 over K2A. And then this is equal to B plus K1 over K2B. So I've added this B to this side and subtracted this A to that side. And then we can factor out the A and B and solve for what these are. So if we pull out the B's, we'll end up saying that B times 1 plus K1 over K2 is equal to A times K1 over K2 minus 1. And then if we divide here by this term, we'll end up with B in terms of A. So to do that, we'll get B is equal to A, and I'll write it as a multiplication. So we have the following. I'm going to pool these terms together. So K1 over K2 minus 1 is the same as K1 minus K2 over K2. And then our following here, our 1 plus K1 over K2 is going to be K2 plus K1 over K2. So we can write that as, since we're dividing, it's K2 over K1 plus K2. And if you multiply these together, of course, we end up with that B is equal to K1 minus K2 over K1 plus K2. So this is that we can rewrite B in terms of A. Then we can go ahead and plug these things in. So if we plug this into our equation, right, we have R, that's equal to the magnitude of B squared over the magnitude of A squared. And so the magnitude of B squared is simply the magnitude of A squared times K1 minus K2 over K1 plus K2 squared, and then A squared on the bottom. So here we've lost all of our constants, and we just have these in terms of the wave vectors, which we know. So we have an expression for the reflection here, how likely it is to be reflected. And we can rewrite this because we have our K's here. And we can rewrite this in terms of energy and the potential barrier to figure out, with actual numbers, how likely are we to be reflected. So to do this, we just plug in the values for what K1 and K2 are, those are back on the slides. I'll go ahead and just write the answer in. So the chance to be reflected is equal to the square root of the energy minus the square root of the energy minus the potential barrier squared divided by the square root of the energy plus the square root of the energy minus the potential barrier squared. And these are just subbing back in the values, right? The only difference, of course, being the energy terms. So subbing in those energy terms for K1 and K2. Now we can also calculate percent transmitted, and the percent transmitted is going to be very similar to the percent reflected. So the percent transmitted we'll write as T, and that is equal to the number of particles that are transmitted per time over the total of the incident per time. And you might have already guessed what we're going to do. This is going to be C star C times K2, which is the speed that those particles are moving, over A star A times K1. And here we have an expression. We already know that C is equal to A plus B. So C is equal to A plus B, and we know that B is equal to A times K1 minus K2 over K1 plus K2. And so this gives us an expression then. We can say that C is equal to A times 1 plus K1 minus K2 over K1 plus K2. And then to get these all under the same common denominator, we multiply the 1 by K1 plus K2, and that gives us A times 2K1 over K1 plus K2. And then we go ahead, we plug this back in, we get an expression for our transmittance. So T is going to be equal to the magnitude of C squared times K2 over the magnitude of A squared times K1. In this case, right, C squared is going to be the magnitude of A squared times 2K1 over K1 plus K2 squared times K2. And then on the bottom, we'll have A squared times K1. Our constants will cancel, and we'll get the following. We will end up, by simplifying this, we'll have 4K1 K2 over K1 plus K2 squared. And just like before, we can write this in terms of the energies like we want to do. And this is going to be equal to 4 times the square root of the energy times the energy minus the potential over the square root of the energy minus the square root of the energy minus the potential squared. And so with these two equations here, I'll go ahead and box them out. We can figure out how likely our particle is to be reflected and how likely our particle is to be transmitted. And again, the important distinction here is that these results don't quite match our classical understanding. So if we go back to the slides, we can see what we'll get here. Okay, so what we see is that as we approach energies that are much higher than the potential, so here at about 2 times higher than the potential barrier, we have almost 100% transmitted. So if we are twice the energy of the potential, most of our molecules, almost 100% of our molecules will clear the barrier. However, if we start to get lower, so at about 1.1 times the potential, only about 60 of our molecules, 60% of our molecules will pass the barrier, and the other 40% are reflected. So we went through this simple and kind of less practical example to show how particles interact with energy barriers. And what we showed is that these quantum mechanical particles, our small electrons, are weird, and they aren't quite doing what we expect them to do. So they said they have a small chance of being reflected by this barrier. Now, combining that with our results for the particle in a finite depth box, I hope you guys at this point will expect that these quantum mechanical particles will do weird things when they interact with barriers. So here we have a small but permanent barrier, and next we want to explore what happens if we have a large energy barrier that's very small in terms of distance. And what we'll see with that is, again, like we kind of would expect, is that our particles have a small chance of going through this barrier that they shouldn't be able to go through. So, for example, we can look at this. So this is what an energy barrier would look like. We kind of model this as a reverse particle in the box. So here we have a particle and it's moving towards this potential box where it shouldn't be. And we want to ask the question, what happens as this particle interacts with the box? And this is going to be your homework problem for tonight, is trying to figure out what happens as this electron interacts with this high potential barrier. And we'll set it up in the exact same ways as we've done before. So over in this area, we have no forces acting against the particle, no potential. We have the free particle motion. In this area, we have the free particle motion, but here we have a large energy barrier. So that's going to be your homework, is to determine, what's going on with this energy barrier. And it's going to be the same as we've seen before for the particle in a finite depth box. Although the applications are different, as we can actually get all the way through this barrier, and then what happens? That's the questions we're going to address tonight. Or not tonight, but in the homework that you'll do before class. So we can look at some examples of this. And again, here we're seeing, I'm spoiling it a little bit, that our particles are going to tunnel through this barrier. And of course, the higher energy they have, the more likely they are to tunnel through the barrier. Another thing that should be pretty obvious is that the smaller the barrier here, the skinnier that is, the more likely the electrons are going to be to tunnel through the barrier. And we might ask what order of magnitude is that? And by going through and solving this problem for the homework, you can actually calculate this. I've shown the answers here. As you can see that it's very sensitive to the barrier width. So here we have a pretty decent, almost 50% chance tunneling probability if the barrier is 0.13 nanometers. And we have a pretty low chance if it's 0.6 nanometers. So the width of our barrier, it's very sensitive to distance. Now, what you might not know off the top of your head, but I'll tell you, is that these distances, so fractions of nanometers, these distances are on the order of the size of atoms. So what this means is that our tunneling, the probability that our electron tunnels, is going to be directly proportional to things like the number of atoms that we have. And if we change one atom, right, if we have a surface that drops down by one atom, our electron tunneling is actually going to be sensitive enough. It's going to be enough to drop it from like 0.16 down to 0.3, and we're going to have a drop in the current. Our electrons aren't going to be able to tunnel as well because we've lost one atom, and we can detect that. So we can use this technique, this is called a scanning tunneling microscopy, to actually see atoms. So here this is done on a sheet of silicon, and you can see the bright spots here are where there's a lot of atom, and then the crevices here are where the atoms kind of fall away because they're actual, spherical atoms packed together. And then you can also see things like ridges and layers of atoms stacked on top of each other, and that's shown here in this rendering of the image. So we can actually use this technique to look at atoms and molecules. A similar technique is going to be atomic force microscopy. So this doesn't quite use electron tunneling, but it uses the same kind of setup. And then what it does is it taps along the molecule. And so we have in figure B a tunneling microscope image of this pentacene molecule. And in C, we have the AFM. And the same with D, but it's zoomed out. And what I want to point out to you is that if we look at C, right, where we're tapping along this molecule, what we see is exactly what we would predict using our good old VSEPR model for bonding. So this experiment actually reveals that our bonding models and theories are correct. We have the same structure of this molecule as what we would predict. Now, what do we do with this STM image? Well, in this technique, we are shooting electrons from our probe into our molecule. And so to dig back into your minds here, going back to organic chemistry, where do electrons go if you shoot them into a molecule? Well, the only place for them to go, right, is the first place for them to go, rather, is the highest or the lowest unoccupied molecular orbital. So they're going to go into this LUMO, and they would come from the HOMO. And so what this is showing us is where the electrons are going. So this is a rendering of the LUMO here for this molecule. Using advanced quantum mechanical calculations, which we'll talk about later in the semester, you can predict the shapes of things like HOMOs and LUMOs. And this is the prediction of the shape for the LUMO for this molecule. And you can see it matches the observed orbital exactly. And so this one's a little bit blurry, so it's kind of hard to make out, but we can see, again, we see very similar lobes in terms of where the electrons are going. So again, our atomic theories, our quantum mechanics are shown here to be relatively accurate and as far as we can show experimentally. Last, I want to mention some implications for tunneling. So tunneling has been not just involved in imaging atoms and molecules, but it's also been implicated in chemical reactions, where there are chemical reactions with really high potential barriers that happen faster than they should based on the energy barriers. And so for these kind of reactions, has been proposed that tunneling plays a role in this reaction, that they, rather than overcoming this activation energy, they can tunnel through this activation energy and react in a much faster way. So this has been shown for things like hydrogen, because if you take a molecule where hydrogen is reacting and replace it with deuterium, that would affect the tunneling greatly, because now instead of a hydrogen atom tunneling, you have a deuterium atom that weighs twice as much tunneling, and that's going to drastically affect its tunneling probability without affecting too much things like how it would move and overcome a regular well. And in this case, we see an example of a proposed model for even heteroatoms, things like carbon, where it's been proposed. I don't think it's been definitively shown for that, though. So this finishes us up for the particle in a box and what we've done with it. So our particle in the box is going to be useful as a tool for modeling many experiments. And even when we move on to more complicated experiments, so we have more complicated boxes like spring potentials and Coulombic potentials, we're going to rely on our particle in a box model to compare it to. It's the most simple model we have. We've shown that the particle in a box, if the box is a finite depth, there's a non-zero probability of being in the classically forbidden regions. And the application of this is that these electrons and other particles can tunnel through barriers, such as a vacuum is what the case for scanning tunneling microscopy is, to give us atomic level details of what's going on the surface, because it's very sensitive distance. And we can even show that tunneling is playing some role, or likely playing some role, in chemical reactions. So I'll end here, and next time we'll pick up by talking about Heisenberg's uncertainty principle. So that'll be the next couple of lectures, and then we'll move on into actual real quantum mechanical problems to look at molecular vibration and rotation and describe those with quantum mechanics.